All right, let's get started. So today is going to be the final lecture of the Bayesian Nonparametric module, and it'll be two more lectures this Wednesday. A guest lecture from Chong Ho on scalable inference model. Scalable algorithms and models. And later on, there will be the final lecture, the closing lecture by Eric on Monday next week. So before we get started, let me just remind you some logistics points. The first thing is that there is a homework for the final homework, and the due date is this Wednesday. And the most important thing is that next week, right after the final lecture, the day after the final lecture, on Tuesday we'll have your project presentations, which will be in the form of the poster session. We booked the NSH atrium from 2:30 to 5, and I noticed that some of you guys mentioned that there might be conflicts with other exams. And if there are conflicts, please email us. You don't have to be there during the poster session the whole time. You can just come by, present our poster, and we'll prioritize the groups that have conflicts. And yeah, you can see on the slide what are the requirements for the posters. Okay. All right. So for the plan for today is basically two parts. First part is the Gaussian processes. We'll go through one of the really famous Bayesian nonparametric models that are widely used. And then, if we have time, by the end, we're going to touch upon some elements of metalearning. And what I actually wanted to get into this neural processes models that were introduced literally last year. And in some applications, they are a pretty viable alternative to Gaussian processes. So they seem to work pretty well. But we'll get to that. All right. So to get started, let's look at this very simple example where we would like to learn a function. And in this case, on the x-axis, we have years. On the y-axis, we have the airline, passengers in thousands. And this is the trend that we have on the graph. And our goal is to predict how would this evolve over time. Right? So it's an extrapolation problem, and there are different ways to make this an extrapolation. So how would you guys go about this? Right. Well, one possible way is probably to extrapolate it in this smooth, nice way, but probably this is not how most of us believe that this curve should evolve over time. Right. We have some sort of prior. We can notice that there are some cyclic trends. There is this linear trend. Probably this is not how a human would make a prediction, right? But if you had some prior to believe that this is the case, or maybe you are not a human, or you had a very strong prior, you could make a prediction like this. So another prediction that is more human-like would be as on this plot, where we just copy and paste the trend, assuming that nothing happened with the airline industry in 1958. This is likely to be the case, right? So we have two possible predictions, right? A human prediction, maybe an alien prediction, and these predictions correspond to certain prior beliefs about how this function should behave, right? And we can then overlay the test data and see how good each of the prior assumption is, and how good the extrapolation is in this case. So what we would like to do, we would like to have a class of models and algorithms that allow us to, just having access to this data over here as points, and pretty much nothing else besides some sort of belief that we can incorporate into the model, or our prior belief, and do an inference and eventually extrapolate, these functions and produce some sort of trend over time. Right? How do we go about this? Right? So it's a regression problem, right? And one way to go about this is to incorporate our belief about the function in a parametric form. Right? One way would be let's say this is a linear trend, we can assume that everything that is the deviation is just noise, and say, well, our function should be linear. Or if we want to have a more complex class of functions, we can come up with some sort of features, which will be or basis functions, right? And have a vector for every x. We'll compute a vector phi of x, and our response function will be the dot product between some parameters w and the feature vector. And we can complicate it even one step further and add some sort of activation function, which brings us pretty much to neural networks, right? So it's a one-layer neural network. And how do we learn this function? So given data and given this functional form, well, the simple way to learn it, and we all learned about it in the machine learning 101 classes, we can come up with some error function or the loss function, and then compute this loss and average over all the points in the data set, and then try to optimize or minimize this loss in order to fit the function, right? So we have a class of functions, we have deterministic error, and we have an optimization procedure to get to the parameters that fit the data the best. But an alternative approach would be, or a probabilistic approach, where instead of coming up with the error function directly, we can come up with a noise model, right? So we're saying that we have a response y of x, which consists of the signal and the noise. And the noise is by assumption unpredictable. So in this case, we'd assume that noise is Gaussian with zero mean and some variance, sigma squared. And we'd assume that the noise is IID. So the noise that is injected in points, in let's say x2 will not affect the noise at points x1 and vice versa. So this allows us to construct this observation model where we can actually compute the probability of the response given the x and the parameters of the function f, right? It's going to be a Gaussian distribution. And since the noise is IID, we can compute the likelihood under this model of the entire data set, right? So it's going to be just a product of all these Gaussians. Now, how do we learn this? Right. We've been doing this pretty much the whole semester. It's one of the popular techniques, maximum likelihood. So we're going to write down this likelihood function. We're going to optimize it with respect to parameters. So what are the advantages of this probabilistic approach? So one advantage is that it clearly allows us to distinguish signal and noise and impose some certain assumptions about the noise. And the other one is that it gives us some sort of intuitive framework that allows us to reason about the uncertainty that is coming from the noise or uncertainty about the model, as we'll see next. But in either of the approaches, we will suffer from some sort of overfitting if the model class is too complex, right? If the model class is too complex, we will be able to perfectly fit the data, and we'll encounter very high error on the test set. So how do we go about solving this? Well, the very standard technique is to regularize the model, right? So in here, we're going to have our loss function or our likelihood function under this Gaussian assumption. It will add some sort of complexity penalty that will control or impose some sort of prior belief about the class of functions that should fit the data, right? But now the question is, like, even if we're searching for a hypothesis in this hypothesis class with minimal complexity and the best possible fit, how do we balance this complexity versus model fit, right? And one way to balance it for a given data set is to try to find this lambda parameter through cross-validation. But the question is, like, is there another way? Is there a more sort of principled way to go about this? And there is a way that is coming from the Bayesian inference literature, right? We're going to use the Bayes rule in this case, or we can use the Bayes rule in this case, and instead of representing this point estimate of the parameters of the model from the class of these functions, we will try to infer the posterior distribution over these parameters. So imagine that we have on the x-axis all the possible parameters that we're looking for, and on the y-axis we'll have this probability of the model. So initially we can have some sort of prior belief about the parameters of the model, and it would be, let's say, some Gaussian. And some parameters are more likely, the other parameters are less likely. After observing some data, we can go and update our belief about the parameters of the model, right? And the belief will sort of concentrate in some smaller area. So with more and more data, the distribution over the possible parameters of the model should technically shrink. And if the model, if the data is coming from, so the data generating distribution is within the class of models, ideally with infinite data we should shrink to a delta function, right? So this is the idea of the Bayesian inference in this case, and we can actually try to represent this whole posterior distribution and work with this posterior distribution if we can. So how do we make prediction, or how do we predict using this posterior distribution over all possible models? Well, one way to do that is basically to integrate the models out. So instead of trying to say what is the, so let me go back a little bit, what is the probability of y given x and some parameters w. Now we're going to integrate parameters w out and just try to find the probability of the response y at the new point, x star, given the data that we observed, right? So coming back to my question about how do we design models that just take into account, just condition on the data that is out there, right, the observable data, and then produce predictions about, you know, other data points, other inputs, other x stars. This is one of the ways where we don't explicitly try to find a particular model, but rather we represent our belief over the space of all possible models, and then we integrate out. Okay? So, in a nutshell, we have infinitely many models. Well, it would depend on the type of this posterior distribution, but if the distribution is smooth, we'll get an infinitely many models that we try to average with some weights, and all these models will be ensembled together in order to produce this prediction y. So the benefit is that the overfitting will be minimal in this case, and this sort of ensemble or Bayesian ensemble of the models will automatically calibrate complexity given the data that we have. So the only thing that we need in order to produce it is this prior distribution. If we have a prior belief over what models are, which is the distribution over the parameter space, then we can compute the posterior and average out all the models over the posterior. And, well, we'll come to this in just a little bit, but typically we're interested in the distribution over functions rather than the distribution over the parameters. So this formulation actually will allow us to get to that distribution over functions, or explicit distribution over functions. Again, just to summarize, so there is this deterministic approach where we have a class of functions, we have deterministic error function, where we're searching for one hypothesis. There is a probabilistic approach where we define the error function through a probabilistic, through the likelihood and the noise model. And then there is this Bayesian approach where not only we're searching for a single hypothesis, but we're searching for the posterior over likely hypothesis, right? Now, In this class, we've seen parametric and non-parametric models, right? And there are examples on the slide. So parametric models could be a mixture of K-Gaussian components, could be polynomial regressions. Neural nets are also in that class. There are non-parametric models as well as Bayesian non-parametric models. And we've considered Dirichlet processes. We looked at the Indian buffet processes, and right now we're going to focus actually on Gaussian processes, right? So this Bayesian inference, where we're trying to represent these posterior distributions in the parametric case, will be just the distribution over some vector space, right? So where every model is characterized by this vector theta, and our distribution is just a multi-dimensional distribution over the vector space. In the non-parametric case, the class of models is much richer. So it could be a model. A model is represented a priori by an infinite set of parameters. But given the data, we do this inference step and arrive at sort of finite parameter model that is suitable for the given data set. Okay? So the inference mechanism in this case is exactly the same. Just the space of objects that we operate on is going to be slightly different. And just to remind you, the process that we considered so far, so we had this process over the probability measures. We had the process over the binary matrices, which is the Indian buffet process. And today we're going to look at this specific process, which is called Gaussian process, which is a process over or a measure over all possible smooth functions. And all these priors, such as Dirichlet process prior, Indian buffet process prior, as well as Gaussian process prior, can be combined with different types of likelihoods. It's interesting that Gaussian process prior with a Gaussian likelihood leads to fully analytical solutions for the posterior, which is very nice. And this is the reason we're going to focus actually on this in the lecture. You can actually combine Gaussian process priors with sigmoid or softmax likelihoods and build models for classification instead of regression. The mathematics will become slightly more complex. You will lose this analytical form, but it's still possible. There are models that are called Gaussian process classification models. So you can look up the corresponding chapters in the GPML book. Okay. All right, so to introduce Gaussian processes, let's first look at at a distribution over functions. And the distribution of very simple functions, which are linear functions with the intercept a0 and the slope a1. So assuming that these guys are distributed according to some normal distribution here, so, we'll get different lines, right? If we sample from this distribution over functions, we'll just get a bunch of different lines, and all of them are going to be distributed as given in the picture. So the shaded area is the denser area, and the white area is where the functions are unlikely to appear. Now, how this distribution is defined is actually through the distribution over the parameters, right? So we defined a0 and a1, and then we impose some sort of distributions on these two. But we are interested actually in the distribution over the functions in the function space. And there is a way to go from this weight space view to the function space view by looking at certain moments of the distributions of these functions at every single point. So what I mean by that, so let's say we have this distribution that is defined through the distribution of the parameters, okay? Now let's compute the expectation of the function f of x at an arbitrary point x, right? If we write this out using the linearity property, basically we'll get expectation of a0 and expectation of a1, and because they are coming from the standard normal, this will evaluate to 0, correct? So at every single point, expectation of f is equal to 0. If you look back at this picture, if you take the expectation, you'll actually get this line, right? Now we can compute the covariance of two random variables. Now the random variables are the value of the function at point xb and the value of the function at point xc, right? These are two random variables. We can compute their covariance. In this case, it will be the expectation of the product minus the product of the expectations. We can further expand that, plug in the actual representation for the function, right? And we'll arrive at this 1 plus xb xc, right? So what we did here is we just basically computed two moments of our function, which is the first and second moment for random variables along the x-axis, right? So we picked two random points, or we picked one random point. We can do the same thing for three random points. You can compute the third moments, etc. But you can convince yourself by just doing a little bit of algebra that, in fact, if you pick n random points here, they are going to be distributed according to some multivariate Gaussian distribution with the zero mean, right? We just computed that. And there will be this K matrix, which will be the covariance matrix of the corresponding F at the corresponding points. And this covariance matrix will have this simple form 1 plus xbxc. And by definition, this is a Gaussian process, right? So we've arrived at the Gaussian process, and we can define, we can state actually the definition more clearly. So a Gaussian process is any collection of random variables such that any finite number of those variables are distributed according to a multivariate Gaussian distribution. And we can write that function f of x is a sample from a Gaussian distribution with mean function, right, m, and the covariance kernel k if we select or pre-select arbitrary endpoints x1 to xn, and we'll arrive at the corresponding multivariate Gaussian distribution. Right. So any questions about the definition? Okay. So that was simple, right? We started with some function. So we started with some simple parametric representation of a function. We defined some distribution over the parameters, and we showed that, hey, if you look at the points or the values of the function at different points on the x-axis, they are going to be always jointly distributed as a multivariate Gaussian. We can look at another example. So this is the linear basis function model. Instead of the linear function, now we have this arbitrary basis functions, which are functions of the vector value functions of the inputs. And we'll assume that the probability so there is some distribution, which is a Gaussian distribution, over the parameters of the model. And parameters is just a vector W. Okay? So we can do the same algebra and basically compute the first moment and the second moment of the function at different points on the x-axis, and we'll arrive at zero mean and this bilinear covariance. Right? And we conclude, again, by definition, that this function, f of xw, is a Gaussian process with the zero mean and the corresponding covariance kernel. And we say kernel because, right, kernel is a function of two arguments, and it can be evaluated at arbitrary points of these two arguments. Right, so you plug in arbitrary xi and xj, you'll get some sort of value. If you plug in n of them, you'll get a matrix, right? Okay, so what is the benefit of actually using this functional view? right? Why do we care about, like, why do we want to work with a functional view of Gaussian processes instead of the parametric view? Sometimes we don't have a good intuition about the parameters. If we carefully design these feature functions and then you know, have this linear form of the function, maybe the parameters are sort of meaningful. But oftentimes, parameters can be less meaningful. For example, in deep neural networks, we don't really know what is the meaning of every single weight in the network. The functional view gives us some sort of interpretability of the model because we can incorporate certain priors into this covariance kernel or the mean function, and I would say that our function behaves in a certain way because the correlations that are captured between the points are according to this covariance kernel with the prior that we incorporated in it. And the other point is that generalization, right? The kernel that we build, the kernel that we use, if we incorporate certain inductive biases in this kernel, and if inductive biases are valid, it allows our model to generalize better and generalize faster, as well as, so for instance, in the example that we considered at the very beginning of the lecture, with the correct kernel, we'll be able to correctly extrapolate the trend of the airline passengers over time. Okay, so from a graphical model perspective, or from a graphical perspective, Gaussian process has this so-called Gaussian field that we haven't seen in graphic models before. So we have, let's say, inputs and outputs. Some of them are observable. So these squares are observable random variables. The circles are latent random variables. We'd like to, given the observations, we would like to be able to make a prediction. Let's say at y star, that is the response value at the x star point. And the Gaussian field sort of is a bunch of latent variables that correlate everything together, right? So if we were to observe, let's say, this f star, then y star would be technically independent of everything else, right? It will not depend on other y's and other x's. But because we don't observe f star, we have to integrate the Gaussian field out. And in this case, all these observable variables will technically affect the response. Okay? So let's go through a few examples, or popular examples, of the Gaussian process kernels. And probably the most popular one is this RBF kernel, right? That defines a covariance function in the following form, where we have some sort of magnitude, a squared, and we have this exponentials, like squared distance, negative squared distance divided by some distance factor, and we exponentiate that. Right. So this kernel is saying, basically, if we have 2 points and they're close together, then they must be correlated. So their distribution should be correlated. And if they are far apart, then because we have this exponent here, they will technically not affect each other. Right. So this introduces some sort of smoothness assumption into the class of functions defined by the Gaussian process. So this is one of the most popular kernels, and these two a squared and l squared are so-called the hyperparameters of the Gaussian process. And maybe one interesting property that I'm not going to prove, but I'll just mention that Gaussian processes with RBF kernels are actually universal approximators. So technically, you should be able to fit any smooth function or represent any smooth distribution over smooth functions with a Gaussian process with such kernel. Okay? So this is just an illustration of how the kernel in one dimension behaves. Right, so we can see that by controlling the L parameter, we can actually control the effect of the points at different distances along the x-axis. And this is how samples from a Gaussian process would look like from the prior. Right, assuming that we don't observe any data, we have some sort of prior distribution, we can sample these functions from the prior. How are we going to sample this distribution? How are we going to sample the functions from the prior? Does anyone know?
Sample multiple points.
Okay. Yeah. So you sample multiple points, and then you can sample the corresponding y's, right, at these points. Because once we fix the points, everything is distributed according to the multivariate Gaussian. So you can just use the multivariate Gaussian sampler with the corresponding k-matrix. All right. So how do we now do inference and learning in this class of models? So what I mean by inference. So once we have the kernel, and once we have the mean function, we define the prior. Now, given the observed data, we would like to go and infer the posterior, right? So let's assume that we have some noisy data, y, which will be different y's at different x's, x1 to xn. And we'll assume also that there is a Gaussian noise around every point. So there is some signal, and then there is a little bit of noise that has this parameter sigma squared. Then we'll impose this Gaussian process prior with some covariance kernel over the functions. And now what we would like to do, we would like to be able to compute f star, right? Or the actual value of the function at the point x star, given our observations. Right? So given the observations, we can condition on any additional point and then get this probability over the values of the function. So a quick reminder of some multivariate Gaussian calculus. So let's say if we have a vector that is distributed according to a Gaussian distribution here, and y1 and y2 are parts of this vector, so we can take a vector and split it into different subcomponents. You can similarly split the covariance matrix into subcomponents as well, or blocks of the covariance matrix. If we would like to compute the conditional distribution of the y1 component of the vector given the y2 component of the vector, so you can use just the expression given on the slide, right? And there is a simple way to prove it. You just work through the calculus. You can actually prove that the analytical form given on the slide is exactly the form that we're looking for. So given that we observed some Gaussian, some random variables, y2 from this Gaussian distribution, we can condition on them and recompute the mean function as well as the updated covariance matrix for the y1 components. Okay. So same thing for the predictive distribution of the Gaussian process. So we assume that now we have a vector of the observations that we had, right, as well as the value of the function at the target point. Okay, so we're gonna just stack them together into a single vector, and can represent this with a Gaussian distribution on the right-hand side. So a priori, we know that our mean function is pure zeros, and our covariance kernel can be split into these blocks. So this block corresponds to the distribution over the observations that takes into account the noise. And then these are the cross blocks, basically the covariance between x and x star and x, and just the covariance between, or the variance of the x stars. Now we're going to use exactly the same mathematical derivation that I just showed you on the previous slide in the recap, and we're going to arrive at the posterior Gaussian distribution. So we know that f star is going to be distributed according to some Gaussian, and in this case, the mean function will take this form, and the covariance function will have the form that is given on the slide. So it's very mechanistic. You can actually go and derive this. It's pretty simple, but it's a good exercise. What we notice here is that we're able to actually compute the predictive distribution analytically, right? Given all the data that we have so far, given the kernel function, we can compute all these matrices, compute these inverses, multiply them together, and we get the actual predictive distribution at this point. So what it tells us is that, let's say we have some data points from before, and after we condition on these data points, let's say we would like to evaluate or get the distribution of the response at the new point x star. So whatever point x star you pick, you can actually get a Gaussian distribution here, right? And you can analytically compute that. And then after, let's say, sweeping through all possible, or maybe through all x stars of interest, we'll be able to get this predictive distribution for every single x star, right? So this is how it looks like in practice. Let's say we have this RBF kernel with some parameters a0 and l0, and after observing just a few points here and here, we can update our belief about the distribution of the function, or the predictive distribution at all the other points. Okay. These functions look a little bit too wiggly, perhaps, right? And this wiggliness came actually from the fact that we chose a very specific L0 parameter, or hyperparameter of the kernel. Right, so if we choose slightly different scale parameter, we can arrive at a much smoother function. Okay? And to compute that, what we need to do is only this Gaussian sort of inference machinery. Everything is analytical. All right, so how do we learn Gaussian process? We know how to do inference. Once we fix the kernel, once we fix the hyperparameters, everything is analytical and good. Now, to learn these hyperparameters, we can write down the so-called marginal likelihood, right? Or the probability of all the responses given the corresponding inputs in the hyperparameters theta, right? So we integrate out our posterior Gaussian distribution. So this is exactly what I mentioned at the very beginning of the lecture. If we want to make a prediction, we can integrate out over the posterior, and that's what we're doing here. So we're going to integrate out this Gaussian process, and we're going to get the distribution over the responses, given the inputs and hyperparameters. And if you work out the math, you'll get this model fit term, the complexity penalty term, that basically depends on the kernel, and some constant here. Okay. And in order to learn or fit this model, we can just optimize this objective function with respect to the hyperparameters theta. So we're going to search in case of RBF kernel, we can search for the optimal scale parameter as well as the magnitude parameter, such that the marginal likelihood is maximized. Okay, and as you can see, so in the previous two examples, these were suboptimal choices of the kernel. Maybe this one was too smooth, this one was too wiggly, but there is a way to find an optimal one. You can see that the error on the points, on these training points or observed points, is actually minimized. Okay, so any questions so far? All right, so just to recap, now we've introduced Gaussian process, we introduced the definition, we saw that everything becomes, when the likelihood is Gaussian and the prior is a Gaussian process, everything becomes analytical and nice. We can learn Gaussian processes or learn hyperparameters of the kernel by optimizing this marginal likelihood, and we can do inference by simply computing a few matrix inverses, right? Now, there is a wealth of literature actually on designing the kernel functions. Because the most important thing in the Gaussian process is the kernel. The way we incorporate our prior knowledge or our belief about how the function should behave is actually through the kernel function. And there is a bunch of standard kernel functions given on the slide that try to incorporate certain properties. For instance, we can have periodic kernels or other types of kernels that would capture our belief. And going back to the example that we considered at the beginning with this linear trend and the periodic function over time, technically we can combine multiple kernels. And we know that this property of the Gaussian distribution is such that if we have two random variables that are distributed according to two different Gaussians, if we sum them together, the result will be jointly Gaussian. So similarly, we can combine the kernels together by taking a weighted sum of different kernels. So there are other kernels that were more specific to the application. For example, kernels defined on strings or sequences, or so-called Fisher kernels. But more recently, there was a large push towards trying to automate the process of kernel selection. Right? All of these guys on the left-hand side are manually designed. Right? We came up with this parametric form for the kernel, and for some reason we believe that it is good. But what if we would like to automate that? Is there a way to automate that? And one way, one recent work, introduced this spectral mixture kernel, where they introduced a pretty expressive kernel that mixes different spectral components together. Have a question? A few slides are where? 25? 35?
It's different, but in the Gaussian process of inference, you had a sequence of steps, and you said start with the standard regression assumption.
Mm-hmm.
Where are we using the standard regression assumption? In the inference procedure.
So you mean here?
The second point, start with the standard regression assumption.
Oh, right, yeah. So the standard regression assumption here, so the question is about the standard regression assumption, is that we assume that we have some sort of signal function, right, f of x, and we have some sort of noise. So this is the standard probabilistic regression, which we started at the very beginning of the lecture. Right? We assume that there is some f of x, and then there is some sort of noise. And noise could be IAD and normally distributed. So that's the standard assumption here. And actually how it manifests in the Gaussian process, it just basically adds this noise term. Right? So we assume that when we have some sort of observations, there will be some sort of uncertainty. So let me show you. So there will be some sort of still uncertainty around the point that is proportional to this magnitude of the noise that we a priori incorporate into the data. But we can learn that as a hyperparameter as well, right? So we learn the scale, we learn the amplitude, and we can learn also the magnitude or the variance of the noise as well. So let's go back to the expressive kernel. So this is the spectral mixture kernel that allows us to capture a bunch of spectral components, right? So you have this, you take the spectral view, you can show that pretty much any kernel function under certain assumptions can be represented as an integral, more generally as an integral, but here we just take a sum over different spectral components over this a bunch of functions of the form as given on the slide, right? And so given this form of the kernel, now we can try to fit the parameters, and the parameter would be the spectral mixture proportions and the parameters of the exponent as well as the parameters of the harmonic functions, right? So once we fix these parameters, now we can do exactly the same procedure that we did for that we would do for any other type of kernel for the Gaussian process, right? So if we go back, we can construct the log marginal likelihood and just optimize it with respect to these parameters. And once we optimize that, well, we can see that the trends that these kernels can produce that fit the data can actually very nicely extrapolate different trends. So it would capture both the linear trend and the nice periodic trend, as opposed to other types of kernels, such as the RBF kernel. So the RBF kernel actually would produce that smooth curve that would go down, if you remember at the very beginning of the lecture. So there are other ways to construct very expressive kernels, and from our group there was a work on deep kernel learning. So the idea is that not only you can represent your kernels in some handcrafted sort of parametric way, but you can also, start with some base kernel, K, and transform your inputs according to some deep neural network. And then assume that your kernel parameters or kernel hyperparameters are all the parameters of this neural network. Right? So what it means pictorially is basically you have this deep neural net part that goes from the inputs to some latent representation, and then this latent representation is basically an input to a Gaussian process. And it turns out that if you build a kernel like this, so this whole construction will be a valid Gaussian process on the inputs. Okay? And actually, it is one of the homework problems to prove that the whole construction is a valid Gaussian process. Okay, but from the architectural perspective, it means that basically by constructing such a kernel, we're injecting a layer that is infinitely wide, right? The more data we have, the wider and more expressive would be this Gaussian process layer. So how do we learn this? Well, we can still construct the log marginal likelihood, and we can try to take the derivative of the log marginal likelihood with respect to the hyperparameters of the base kernel, right? So it will be the derivative of the objective with respect to the kernel matrix, and the derivative of the kernel matrix with respect to the hyperparameters, as well as we can compute the derivative with respect to the parameters of the deep neural net. And here we're just using the chain rule, right? So we take the derivative with respect to the kernel matrix. Kernel matrix is a function of this deep neural net here, G. So we'll take the derivative with respect to the activations, and then we'll take the derivative of the activation with respect to the parameters. So it's just a chain rule that we can apply in this case. And to make this whole construction scalable, right, we may use inducing point methods, and we'll come to that in just a second. But these processes can be as scalable as arbitrary deep neural networks, even though the layers that we construct for them, or the GP layers, are sort of infinite layers. So this is the results from the paper that introduced deep kernel learning. And if you look at the results, they combine the spectral mixture kernel as the base kernel with some deep neural net. In this case, they looked at the multi-layer perceptron. And what it turned out is that the RMSE error, or root mean squared error, on these regression tasks was much lower than the ones that was obtainable by a standard GP. Okay. So if we deal with sequential data, is there a way actually to use the same trick, right, and represent a kernel over sequences? Or can we have a valid nonparametric model over sequences? So the answer is yes, and we actually wrote a paper a couple of years ago where we introduced this deep kernel learning with sequential structure, where basically you inject this nonparametric Gaussian field, or this infinite layer, into a recurrent neural net. As you can see here, your recurrent neural net computes some sort of representations over time, and then these representations are fed in to the Gaussian process, and then you build just the base kernel on top of that, and then you can make predictions. So basically this Gaussian process layer would correlate the outputs throughout time for you. So not going into the math and how to do that. So to construct the model like this is pretty straightforward. So you just come up with an RNN. RNN computes you the latent representations. On top of latent representations, you build a base kernel. So it is pretty straightforward. The optimization part is a little bit tricky. You need to be able to optimize this model in a stochastic manner. And our contribution was to introduce this stochastic learning algorithm for this class of models. So these are some results. So we applied it to lane prediction data that was coming from a self-driving car. So a car was driving on the street and was recording the lanes. So we tried to estimate what would be, how would lanes behave into the future, right? So we were trying to predict basically the position of the two lanes on the street from the data. And we use this Gaussian process model with this recurrent kernel. We're able to not only get the prediction as with the standard LSTM, so you can see that predictions could be arbitrarily good or arbitrarily bad, but we can also get some sort of estimates of the uncertainty or how certain the model is that the lane is actually going left or going right. Similarly, we applied this to lead vehicle position prediction, right? And there was this, on the x-axis, this is the basically distance left or right from the car in meters, and on the y-axis you have the distance in front of the car, and you're trying to predict where is going to be the next position of the vehicle that is in front of you, given some sensor inputs from the car. So you don't observe actually where the vehicle is, but you have some sort of sensor inputs, and you have the initial position you're trying to predict the next position given your sensory observations. So Gaussian processes with LSTM structured kernels allow us to capture the uncertainty pretty nicely in this case. All right, so I already mentioned that there is some scalability issues with these models, or at least potential scalability issues. And the problem is that in order to compute these nice analytical form of the predictive distribution, we need to do inference that requires a matrix inverse, right? And then for learning, we need to actually compute this log determinant part, right? Both of these are, O of n cube, right? So this is problematic because if the number of points, as in all recent data sets, are beyond thousands, but is around like millions or even billions, billion cubed is problematic to compute. It will not be possible, right? So how do we scale these models? And that's been a very active area of research for the last few years. So there are basically three families of approaches to scalability. So one of them is we try to approximate the kernel in some dual space, right? So I already mentioned the spectral space of the kernel. So instead of representing the kernel as a having the continuous representation in the spectral space for the kernel, we can actually sample points in that spectral space and come up with an approximation that is more tractable. So there are methods that are called inducing point methods that are pretty popular, and I'm going to explain how they work in just a second. And then there are also methods that exploit the structure of the kernel matrix. Because we are designing, in some sense, the kernel matrix, technically we can introduce some sort of structure that later on will allow us to compute these inverses as well as log determinants very efficiently. Okay, so and the two structures that people use often is the Toeplitz structure and the Kronecker structure. So how does the inducing point method work? In a nutshell, let's say we have a Gaussian process over n points. So we need to represent this covariance matrix over n points. And generally, it could be pretty dense. But instead of the dense representation, we can actually try to find an approximation of this matrix through this decomposition, where we decompose the dense large matrix into tall and thin, and then this very small matrix, as well as wide and short, right? And then in order to compute the inverse, we'll basically reduce to computing the inverse of a very small matrix. And intuitively what it means is that when we introduce such a decomposition and when we invert this inner matrix, basically we can show that this will correspond to building a kernel on a small subset of virtual points, right? So we can select these m virtual points and then use these m virtual points that we sort of induce into our data set in order to be able to compute a very nice approximation to the original kernel matrix. So broadly speaking, these points would depend on the data. So the best possible approximation, if we would like to get the best possible approximation of the kernel matrix, we would like to select a subset or a small set of points such that the error of the approximation is minimized. So alternatively, not only we can select the points that are nicely approximating the kernel, but also that have some sort of structure so that this km minus 1, right, this inverse of the inner matrix, is also computed efficiently. And in this case, we can use some sort of Kronecker structure. So here's an illustration. So the inducing points on these two figures are presented by these little circles. And if we put them on a grid, for example, on a grid that captures all the, let's say, points in the data set, we'll be able to approximate the kernel through this decomposition pretty efficiently. And in order to compute the inverse, because the points are on the grid, we're going to exploit this grid structure. And in fact, we can speed up computation almost to, and get to linear time approximation. Okay? So there's one little caveat that everything looks nice in low dimensions. In high dimensions, if we would like to have a very accurate representation of the kernel matrix, we'll need a lot of inducing points. Right? If we'd like to put inducing points on a grid and the dimensionality is d, so with the dimensionality, the number of inducing points that we need total will grow exponentially. So let's say we need k inducing points per dimension. In d dimensions, we will need k to the d. And so this is a little caveat, and this is something to keep in mind. So Gaussian process approximations work best in low dimensions. Okay, and this is just figures that show you this linear sort of scalability of training with the number of epochs for deep kernel learning, as well as pretty much of1 inference, where we pay constant time per data point in the test set when we do inference, both to compute the mean prediction as well as the variance. All right, so more recent work that just appeared actually on arXiv, and this work is from Andrew Wilson's group, where they actually scaled exact GP inference to millions of points by using GPUs. Actually, a few years ago in the class, we had this suggested projects to try to port Gaussian processes to GPUs, and I believe none of the teams tried to tackle this problem. It was pretty challenging. So finally, they managed to do that, and they scaled Gaussian processes literally to millions of points on 8 GPUs. And to put this into perspective, in order to compute the predictive distribution or the posterior distribution for the Gaussian process on 1 million of points on 8 GPUs, they ran that for about 3 days. So it is still pretty slow, but it is very exact. And the point of the paper was that not only you can do that on GPUs, but also exact inference in Gaussian processes is often far superior compared to approximations. So they tried to compare exact inference of GPs with all these like fancy inducing method points and approximate inference. And they show that the exact GPs are far more superior on a bunch of data sets. Okay. So finally, if you would like to use Gaussian processes in your own research, or maybe to solve some of the problems that you have, there is a bunch of libraries that you can use. So the most popular one is probably the one that comes with the book, GPML book, the corresponding GPML library. It's a nice implementation of Gaussian processes, but it is in MATLAB, so it's a little bit kind of outdated, but it's still supported as far as I know. In our group, we've designed a Keras-based Gaussian process layers that allow you to build the layers that I just told you about with or infinite dimensional layers and interface them with Keras, and all the backends that you can use for deep learning, you can use them with. More recently, there is this GPyTorch, the PyTorch-based library that allows you to pretty much do everything that you want with Gaussian processes and still work with PyTorch. So all the recent scalable methods, as well as this exact inference for Gaussian processes on GPUs, is supported by this library, which is very nice. The previous two libraries did not support GPs on GPUs. Okay, and as well as TensorFlow has a sublibrary that allows you to have Gaussian process layers, as well as a lot of other Bayesian layers. Okay. So any questions so far? No questions. Okay, just to summarize. So what we've covered in this lecture was Gaussian process, one of the most popular, I would say, Bayesian non-parametric models these days. Dirichlet processes and Indian buffet processes used to be pretty popular and used to be a very active area of research. I'm not sure how much they're used these days, but Gaussian processes are still used both in academia and industry, and they're pretty popular in a lot of applied research problems. So what we saw is how to define Gaussian process. We started from standard regression problem. We introduced the Bayesian regression. We introduced the Bayesian inference for regression, and then we switched from the parameter view, where we had the distribution over the functions induced by distribution over parameters, to completely the functional view, and connected that with the covariance function and the mean function, right? And then we looked at the inference. We saw that inference can be done exactly and analytically for Gaussian processes with Gaussian likelihoods. It requires some sort of scalability, right? And for that, we need to use some sort of approximate methods, or we can scale it by parallelizing on GPUs. And yeah, there are multiple libraries that can be used for Gaussian processes. Let me see. So how are we doing in time? Okay, so we have maybe 10 more minutes. And let me quickly introduce you to some of the elements of metalearning and show how that is related to Gaussian processes and all that. But before then, any questions about Gaussian processes? Because this is pretty much the final step of the Bayesian nonparametric module. All right, no questions. So let's just dive into this example, right? Where we would like to learn functions, and in Gaussian process, we wanted to learn a function. We assume that there is a function that generated the data, right? We didn't know what the function is. We imposed some sort of prior over the space of all possible functions, and then, we developed these, pretty much linear algebraic methods for learning and inference. Now the question is, what if the data is generated not by a single function, but maybe by multiple functions? And imagine a situation where you have a multi-round kind of regression problem, where the first round starts, and you get a bunch of points, maybe just a few points, and you would like to learn a function, or to extrapolate the function, that corresponds to these points. And then the round finishes, you get your score for these predictions. And then the next round starts, and you get another function that potentially generates some data points, and then you'd like to learn that specific function. So we'll go through the examples where this could be interesting from the application perspective. But on the slide, just look at this figure where, let's say, we have a bunch of sinusoids, and every single round, what we'll get one of these sine functions that will be represented by a few points. And we would like to approximate the sine function given just a few points. So if you take all the data generated by all the sine functions together, and they are all different in the amplitude and the phase shift, so all the data will basically cover the entire block, right? The optimal prediction, if we don't know where the points are coming from which sine function, basically will be all zeros, right? But in this case, if we know that the data is coming in from different functions, we can condition only on the subset of the data set of the data and try to approximate every single function separately. Okay. So let's slightly formalize this and see how we can define this formally. So far we looked at these prediction tasks that on the slide I call standard learning, right? Given some data set, we know that it comes from a single function. We would like to learn, let's say, parameters or some sort of representation or predictive distribution given this data from a single function. But assuming that we have a distribution over all possible functions or a distribution over tasks, we can try to pose the problem as learning to learn, which means that if we know how to learn a single function, can we translate the skill of learning to be able to learn other functions that are similar to this function? Right, the only assumption here is that all our tasks are coming from some sort of distribution over tasks. So all our functions are somehow related. So there is some sort of shared representation between these functions. And given that we know how to learn some of them, can we use that learning algorithm to learn the other functions? Okay. So we can define a distribution over tasks. We can define the so-called adaptation rule. And we can try to generalize. So given a task description or given something that describes which function this is, right? Can we try to produce a model that would approximate the specific function? And in this new setup, the loss will be computed in expectation over the distribution over tasks. Okay? All right, so we have a distribution over tasks. Within the task, we have distribution over observations, or maybe inputs and targets, as well as we'll have this G function that takes in the task representation and produces some sort of maybe parameters or some sort of representation for the function that we're trying to fit for this particular task. Right? So the only difference between the standard learning and the learning to learn is that learning to learn is learning on a distribution of standard learning problems. Right? If you want to think about this more formally, but just to give you a few examples. So one of the popular examples that's been explored in the literature in recent years a lot, a so-called few-shot image classification problem. So the setup is the following. Now, instead of having a single data set where you have a bunch of examples that describe different classes and you're trying to learn a function that can predict which class the object is coming from, now we have a bunch of data sets, and every single data set is a small, small data set of, say, one example per class, and then you have the training data and test data. And within the data set, your goal is to learn on these few examples per class of the training data, and then test your model on the few examples on the test set. Right. So basically, given that all these data sets are sort of images that are coming, let's say, from ImageNet, there is some sort of sharedness, or the functions, the optimal predictive function or optimal classifiers for every sub-data set, they have some sort of shared components, right? But all these functions are different for every single data set. So what we would like to do, we would like to be able to come up with this procedure that given one of these data sets with a few labeled training examples produces me a good classifier, or parameters for a good classifier, or maybe a function that is a good classifier. Similarly, we can do the same trick for regression. So a more realistic example would be few-shot user-specific recommendation, right? Where in this setup, let's say we have a bunch of users, and every user is described by the history of their activity. Let's say on Twitter, they like different posts, and every single user will have slightly, the positive classes and negative classes, what they liked, what they disliked. And similarly for the other users. So what we'd like to do, we'd like to be able to condition on these points and produce a function for every single user separately, right? A function that would be predictive for this specific user, what the user would look like, would like, or what the user would not like. Okay? I believe Eric already mentioned this. The contextual interpretability is another example where instead of, so in all previous examples we had these small sub-data sets on which we condition to produce a function. So here we can condition an arbitrary data modality. We can condition an image and produce an interpretable linear model that can be further applied and used for prediction. And another example is from robotics. So it could be, there's this task called one-shot imitation learning. I believe I covered imitation learning before. So, and the one-shot imitation learning, not only you'd like to be able to imitate a single behavior from a bunch of demonstrations, but given a new demonstration, you'd like to be able to condition on that demonstration and produce a policy that can quickly, imitate that demonstration. Right. So all these are examples where this setup, or meta-learning setup, makes sense. But let me go back and just ask you any questions about the formal setup, right? The distribution over the learning problems. Okay, so I guess in the last 5 minutes, I'll cover conditional neural processes that try to actually tackle this setup and propose a certain, random process to do that. So in the so on the slide, you can see that in the standard, regression or classification problem, so we're given a bunch of observations, and for the corresponding observations, we have inputs and targets, and what we'd like to do, we'd like to be able to make predictions for a bunch of inputs that we don't have observations for, right? We can use a Gaussian process for that, or we can use something else. But basically, what we do, we train on the data for which we have the response variables, and then after training, we get this G function, right, that we can plug in and apply basically to every single test point. So the idea behind neural processes is that, or conditional neural processes, is that we can combine the two parts together. So basically, we'll try to condition on these observable data instances, data points of inputs and targets. For every single data instance, we'll learn a representation R, and then we'll aggregate all these representations and provide them as some sort of contextual variable that will feed into the function G. So that given different sets of training data, we can technically produce slightly different functions, G. Okay? And this is something that reminds the inference in a Gaussian process. So given different x's and y's that are used for training. We can condition on them, and then we can infer the posterior, right? So in the Gaussian process case, the posterior was represented through this, posterior kernel, posterior mean function, correct? Here, the posterior is basically represented by this context vector R, okay, that you explicitly condition on, and then you use some sort of parametric function G. Okay, so it's some sort of parametric approximation to a Gaussian process, and you can actually compare them to Gaussian processes, right? On a simple regression problem on the right-hand side, the red curves correspond to the Gaussian processes that are, or to the posterior distribution of the Gaussian process with, I believe, RBF kernel here, and you can see that you can perfectly fit the data points you condition on, but maybe not so perfectly fit the areas that you are not, you don't have points at. And that really depends on the kernel, right? If the kernel has not been selected or learned correctly, your Gaussian process will always underfit the areas where you don't really have many points. What neural processes are allowing you to do is to basically to be able to capture implicitly this kernel through this conditioning process. So this conditioning process that is given on the slide allows us to somehow implicitly represent the kernel. The interesting part is that you not only can use it in simple one-dimensional regression problems, but you can also try to use it in problems such as image infilling, where you condition on the values of certain pixels, and then you try to predict the values of other pixels. Right? And you can perfectly sort of denoise images or reconstruct hidden parts of the images. To do that with a Gaussian process would be pretty hard, because you would need to come up with a pretty elaborate kernel that captures certain features of the images, and that is not possible. I mean, it's pretty hard with a Gaussian process. Neural processes allow you to do that much easier. All the neural processes are not proper Bayesian non-parametric models. They are parametric. All right, so there are more recent models that are called attentive neural processes that incorporate also attention inside, the attention mechanism inside the neural process. So instead of using these MLPs that produce the context vectors, right, we can use some sort of attention mechanism that would attend to different parts of the context data set, and then produce the context representation that will be further used down the line for prediction. Right. So the reason why this model was proposed is that people noticed that neural processes tend to underfit the data, and even though we have, a bunch of points here and there, after training, after the model converged, so it's still not able to actually predict some of the points. Right. So this is one of the limitations, and perhaps the model is not expressive enough. This will not be the problem with Gaussian processes in this very specific case, in 1D. In case of images, that tends to produce sort of blurry approximations, right? So attentive neural processes technically rectify that, so they allow you to have much sharper images, much sharper representations. All right, so, in conclusion, this is just the summary of what we discussed so far today. So we covered mostly Gaussian processes, and at the very end, we touched upon this new class of problems called few-shot learning, or metalearning, and metalearning techniques that are used to solve these few-shot learning problems. And there are certain setups, certain practical problems where the setup makes sense. All right, I think that's it for today. So in the next lecture, we'll have a guest lecture, and we'll start that will basically open the final scalable models and inference module. Okay?